Okay. Good afternoon, everyone. So first of all, I would like to thank you for enrolling to this workshop to verify or not to verify microbiome data. What are the alpha diversity metrics? So briefly, I will talk about us. So Winter Genomics is a Mexican company that focuses in the analysis, the informatics analysis of data. We have a lot of things that we can do and help you with process, but I'm not going into deep detail with this information. So we are very happy to be here and to give this workshop. I would like to thank you also the European Conference of Computational Biology that give us this space to teach you how to analyze a little bit of the microbiome data. So this workshop will be divided in two sections, in the practical and theoretical. I'm going to start with the theoretical session, and the practical session the first practical session is going to be led by Nayeli, and the second practical session is going to be led by Violeta. Kenya is here also to help us if you have any question during the workshop. So I think that's all. First of all, I'm going to start with the overview of this workshop. So in this workshop, mainly we are going to talk about what's a microbiome project, their aims, general structure, and the bioinformatics results that you get in this microbiome project. Then we are going to move on to the rarefaction. I'm going to give a little bit of details about what rarefaction is, its definition, how does it work, and some current discussions that there are in science about rarefaction, if it's going to be useful or not. And then we are going to move to the first practical session led by Nayeli. And then we are going to be back to the theoretical part of the alpha diversity. We are going to start talking about its definition, important concepts of alpha diversity, and what are the indices normally used to measure this. And then we are going to move on again to the practical session, in this case led by Viole. So let's start with what is a microbiome project. So the aims here is first, who are they in terms of which microorganisms are in our sample? So this question could be answered by the taxonomic composition. The second main question is how are these communities structured? So in this case, we can use the alpha diversity and the beta diversity indices to answer these questions. But as I mentioned in this tutorial, we are going to focus on the alpha diversity metrics only. So how does a microbiome project start? So in this slide, you can see like the general structure of the experimental part of a microbiome project. So you start with a question about the ecological nature of a microbial community, and you start with the sample collection. Then once you have the sample, you are going to extract the DNA, and then you are going to amplify a region of interest. In this case, the region that is usually amplified is the 16S RNA, or it could be some other region like the 18. Now that you've amplified this data, you normally send the sample to a sequencing company so that they can perform the library construction, and then they will do the sequencing part. So you will have as an output the FASTQ files. And these FASTQ files are the ones that contain the sequence and the quality control of each nucleotide. Then let's move into the bioinformatics part. So as I said, once that you get the sequencing output, you get two FASTQ files, one from the reverse and one from the forward, sorry. R1 is forward and R2 is the reverse. And these sequences are denoised and grouped on features. So these features could be ASVs or autos, depending on the aims of your project, but in this workshop, we are going to use the generic features. So then we move into the, we need to know that these sequences should be denoised and grouped on these features that I already told you. And then we move on into the taxonomic classification. So this could be one step follow after the denoising and then the phylogenetic tree. So once that you have all this information, you can move into the ecological analysis part. So it's important to highlight the results that we usually get from the bioinformatics analysis. So we have 4 files that are relevant to this whole process. The first file is the metadata, and it's a file that you create by yourself. Then the second file is the feature table that is obtained from the denoising and clustering process. Then you will move into the taxonomic table that, as its name says, it is obtained from the taxonomic classification, and then you will have the phylogenetic tree that is a NeoWig format. So once that we have all these files, we can perform the ecological analysis successfully. So I'm going to explain a little bit each one of these files, starting with the metadata file. So as I said, it's a table that you create by yourself. So it contains the sample IDs and some description that it's relevant for you to notice about each sample. So in this case, we are showing the accession number and the sample type. Look that the sample type, in this case, we have normal tissue, but with the dataset that we are going to use in this workshop, you will also have cancer tissue. Then the second file is the feature table. This feature table contains the sequences that are found per feature. So remember that the features could be ASVs or JOTUS per sample. So for instance, from feature 1, in sample number 1, we found 40 sequences. So from the same feature 1, in sample NT06, we found 58 sequences, and so on. Another important file is the taxonomy table. And well, as its number says, it has the taxonomic classification of each feature. So it will start from the domains until the species, but just be aware that in some cases you are going to find not available data of some features. And finally, the last file is the phylogenetic tree that in this case, the nodes are going to represent each feature. With all this information, we can move into the ecological analysis. So the minimal things you must report when you do a 16S microbiome project are shown in this slide, starting from the taxonomic composition that could be represented as stack bar plots or heat maps. Then you can do the diversity analysis that could be alpha diversity or beta diversity. In the case of the alpha diversity, you can calculate the rarefaction curve, and you have some indices that we are going to talk about later on this tutorial. But you also have the beta diversity analysis that is through the distance matrix and clustering analysis. Okay, so now let's move into the rarefaction. So we have now some context about the ecological analysis of a microbiome project. But as I said, rarefaction is part of the alpha diversity analysis. So in this section, I will discuss some key ideas explaining how does it work and why is it important. First of all, the rarefaction is a method that adjusts for differences in the library sizes across samples and allows alpha diversity comparisons. Rarefaction involves selecting a specific number of sequences that are equal to or less than the number of sequences in the smallest sample. Then, sequences will be randomly selected from large samples until the number of remaining sequences reaches the threshold. And finally, the number of features, remember that features could be ASVs or OTUs, are determined from the selected sequences. Okay, but how does it work? Well, imagine that you have an experiment with 3 samples and you already know the number of sequences of each sample. And for instance, in this case, sample number 1 has around 93,000 sequences. Sample 2 has around 25,000 and sample 3 has around 64,000 sequences. But you want to know how many features are in each sample. So we have to consider that if one sample has more sequences, the probability of finding more features is higher than the samples with fewer sequences. So think about gold. Imagine that you are searching for gold in some area and you only have 1 yard to look for the gold, but your friend has 1 mile. So which one of you has a higher probability of finding more gold? In this case, it would be your friend because he has 1 mile. So here is like the same situation. We must adjust library size differences across samples to properly make the alpha diversity comparisons. So how do we adjust library sizes? To start, we will choose a number that is equal to or less than the number of sequences with the smallest sample. So in this case, it's sample number 2 because it has around 25,000 of sequences. So we are going to select 25,000 sequences. Now, we will determine the number of features in 25,000 sequences in each sample. So let's imagine that in sample number 1, around 93,000 sequences are present in this sample and are represented in this space. So each of these lines represents this number of sequences, and from all these sequences, the 25,000 that we previously selected are highlighted here in red and are randomly selected, right? So this would be like the easiest way to represent or to explain how the sequences are randomly selected. But in the real world, selecting sequences is repeated at least 10 times in a different number of sequences or depth. So these repetitions are subsamples. So here we go. First, we have sample number 1. That is the one that has around 93,000 of sequences. And that is their original size. And the algorithm is going to make the first subsample at sequence number 1. In this first sequence, the algorithm finds one feature, and this is going to be repeated. Then, let's move into the second subsample, that in this case, the algorithm selected around 2,000 sequences. And at this number of sequences, the algorithm found 655 features. And it's going to be repeated, the subsample, at the same number of sequences. As you can see here, the number of sequences in the subsamples increase until the number of sequences we choose, that in this case is 25,000. And we choose this number because, as you remember, it's equal to or less than the number of sequences in the smallest sample. So, as you can guess, with this data, we can obtain an average of the number of features that the algorithm found in each subsampling process. And with all of this, we can construct a rarefaction curve. So we will have everything that we need to plot this curve of our samples. So the number of sequences of each subsample is going to be on the x-axis, and the average number of features is going to be on the y-axis. So again, in the first subsample, we have the number 1, and on average, we found 1. So we are going to plot it here. On subsample number 2, that we have had 2,000 sequences, more or less, we found 656 features. And we are going to plot it here at this point. In subsample number 3, with 5,000 sequences, we found on average 800 features, and that is going to be plotted here. and so on. So this process is going to be repeated through all the subsamples to get this rarefaction curve. But here we just have to consider that we are just representing the sample number 1 that has around 93,000 sequences. Okay, but what about the other samples? So the other samples need to pass this same process to finally get a plot that is similar to this one. But the next question is, how are we going to interpret this data? So we are looking for sampling process to capture all the organisms that are represented by features of the sample. So this is going to be represented by the asymptote, meaning that the curve of a sample should be parallel or almost parallel to the x-axis. So in this example, we see that the sample number 2 is close to the asymptote, which you can see that it shows a slow increase since the third subsample here. So we can say that since 5,000 sequences, the number of features is steady. So if we compare this against sample number 1, we see that in case of sample number 1, the curve is still increasing. So what are the current discussions about rarefaction? So we could say that it has the advantages and disadvantages, and in this case, the rarefaction is not an exception. So there are many discussions about using this method, which all of them are very good points, but we would like to take them as warnings instead of no's. So the first warning would be that rarefaction involves the omission of available daily data because the process of selecting a specific number of sequences implies deleting other sequences. So this could be a problem if your smallest sample has 100 sequences and your biggest sample has 10,000 sequences, but you are going to verify at 100 sequences. So in this case, you must make a crucial decision. What do you prefer? Do you prefer losing information in terms of feature and diversity, or do you prefer to lose a sample? The second point is that rarefaction doesn't account for measurement, for the measurement error, meaning that when we perform an statistical analysis, we always consider the measurement error of an equipment if we are doing like wet lab or something like that. Whereas in the microbiome project during the analysis, we never do that. Third, the statistical power of the analysis will depend on how much data is removed. And this point is very related to the first one that I mentioned, because if you make a wrong decision about the number of sequences, then your alpha comparisons will be invalid. And finally, the strongest point is going to be the nature of data. So in microbiome projects, we work with compositional data, but much of this analysis that we develop derives from methods of continuous variables. It implies that these analyses already have an initial bias. But despite all of these points, the rarefaction is our best option because there aren't other viable alternatives. Rarefaction is still the most popular method to standardize library sizes. Okay, so I think I just talked a lot. So before going into the practical session, I'm going to talk about the paper that we chose for this workshop. That is the analysis of changes in microbiome compositions related to the prognosis of colorectal cancer patients based on tissue-derived 16S rRNA sequences. If you would like, also we can share you the link of the paper. And in this paper, the authors compared the microbiome between two types of tissues, the ones with colorectal cancer versus the healthy controls. So the original paper has 100 samples, but in this case, we randomly selected 40 samples, 20 for colorectal cancer and 20 from healthy tissues. And okay, so before we go to the RStudio practical session, If you would like to join with us, open your RStudio, and I hope that you've been able to download all the data that we sent you by email and all that you successfully installed all the libraries. If you face any problem, you can write us on the chat and we will try to assist you. If you, on the other hand, prefer just to follow the workshop and then do the practical session by the end or maybe tomorrow or whenever you want, it's okay. So yeah, I think it's all. Before we are going to move into breakout rooms, there are going to be 2 breakout rooms. Please, everyone go into the general breakout room. So I think there was one other question.
Yeah.
But in the meantime, I think we are going to continue, and then the one, I think I don't want to mistake the name, but if you could please write it on the chat, it would be easier for us to answer the question over there and then continue while we continue with this the other part of the session, right? So, okay, I'm going to share my screen. Okay. So now that we've back from this practical session and that you understand or have a better idea what is a rarefaction analysis, we need to move into the alpha diversity analysis. So for this part, first I'm going to explain the key concepts about what is alpha diversity, and at the end, which are the indices, the metrics, and so on. So first of all, what's the definition? In simple terms, we can say that alpha diversity describes the species diversity within a community at a small scale or local scale. So for instance, in this image, we have two biological systems, the system AB and the system CD. In both systems, in the system AB, there are two sites, the site A and the site B, whereas in the system C, in the system CD is the site C and the site D. Okay, so these sites could be different among each other in terms of salinity or the implication of two treatments or whatever you are studying in your project. So according with this image, we can say that the alpha diversity describes the species diversity within a community, that in this case, that I'm pointing site C, and it's at a local scale or site. On the other hand, the beta diversity allows the comparison between different sites. In this case, I'm pointing the differences between site A and site B. And finally, the gamma diversity describes the diversity between the two whole systems, that would be in this case system AB versus system CD. So here I mentioned an important concept, that is community. So what's the difference between a population and community? It is crucial to distinguish between these because a population is a group of organisms that belong to the same species. So for instance, in this case, we have that the population would be these same green microorganisms that I'm representing in the same color, whereas in contrast, the community is going to be a group of organisms of different species. So communities are the target of interest in our microbiome project. So we must think that each sample contains a community. So another important concept is the richness. So the alpha diversity metrics are based on two things, richness and evenness. Richness is the number of species in a standard size sample. Think that a sample represents a community. So for instance, we have a community with some microorganisms that are represented in different colors. And in this case, we can see that species number 1 is represented in color green, and it has 4 specimens. Then species number 2 that is represented in yellow, it has 3, and so on. So in this community, it's important to keep in mind that in communities we have differentiated species and different number of individuals of each species. So richness, despite this, we're still using the term species, but just remember that in the microbiome project, we don't have species, we have features. So in this case, in this one, we have the feature number 1, we will have the yellow would be feature number 2, and we have 3 individuals, and so on. Then another important concept is the relative abundance. So to understand the concept of evenness, first we need to talk about the relative abundance. So it is the proportion that each species has in a community. So the formula to calculate this relative abundance is pretty easy. You just have to divide the number of individuals of a specific species between the total individuals in the community. And that's it. So for instance, if we go back to the small community that we create, we have 4 species, one, the green, yellow, red, and brown. And we already know the number of individuals that we have in this species. So if we count each of these individuals, we have a total of 13. So in order to calculate the relative abundance, we divide for species 1, 4, that is the number of individuals that we have in this species, between 13, and we get 30. 0.30. It means that 30% of the community is composed of these green microorganisms. We will have to repeat this operation with each one of these species. And if we do the sum of all the proportions, we will obtain a number equal to 1 or really close to 1. In this case, we obtain 0.99. So now let's talk about evenness. So the evenness or equitability of a community implies the equality in the number of species. We could detect this with the relative abundance that we previously calculated from each species in the community. So if the proportions are similar as the ones shown here in community number 1, it means that there is evenness in the community. But on the other hand, if the proportions aren't similar, as we can see here in the community number 2, where we see that species number 3 is pretty dominant, well, it implies that this species dominates the community and there is no inequality or equal distribution. So, as I said, alpha diversity metrics summarize the structure of an ecological community concerning its richness, its evenness, or even both. So in this table, I'm representing the summary of some of the most popular alpha diversity indexes. And they are classified based on their more relevant characteristics. So in this workshop, we are going to review the Shannon Index, Pilus Index, and Gini-Simpson Index, because these ones are the most popular through the microbiome projects. So let's start with Shannon Winners Index. This part is going to be a little bit of equations and formulas, but please don't panic. We are going to move on into the practical session where you are going to learn how to calculate these indices like really easy without writing these formulas, but it's important for you to understand how these indices are calculated, right? So this Shannon Winners Index was initially developed for the communication systems, and it's based in the information theory. So in microbial ecology, it is used to calculate the alpha diversity through the richness. So this Shannon Index is equal minus the sum of the species proportion multiplied by the logarithm base 2 of that proportion. So how does it work? How to get this Shannon Index into the microbiome project? Well, first of all, this algorithm is going to use the feature table that I described at the beginning of this workshop. Remember that this feature table will contain the number of sequences, and think about the sequences as individuals. So it's going to contain the number of sequences per sample. Remember, samples are NT02, NT09, and per feature, feature 1, 2, 3, and so on. So just also keep in mind that features are species. So from this original feature table, the relative abundance is going to be calculated the way that I previously told you. So with this information, we can calculate the Shannon index. In this case, we can notice that the proportion of features in the community of sample number 2, NTO2, are similar. So in this community, we can say that there is evenness. Plus, the community shows a higher diversity than the community in sample NT09. Another index is the Simpson index, and it is easier to understand because it measures the probability that two individuals or sequences are randomly selected from a community that this randomly selected species will belong to the same species. Feature. So how does it work? Again, we start with the feature table to calculate this Simpson index. And this index is going to take the number of sequences of each squared feature, and it's going to divide it in the square number of sequences. And then it's going to sum all of those results. In this case, if we take two sequences from sample number 2 that I'm showing here, the probability of both belonging to the same species is 0.3. The third index is Gini-Simpson index, and it derives from Simpson index. So it derives from the Simpson index, but also it's the opposite of it. So this Gini-Simpson index measures the probability that two individuals or sequences randomly selected from a community will not belong to the same species. So as you can say, is the opposite to the Simpson index. So if you understood the Simpson index, then Gini-Simpson would be easier to understand. To calculate this index, we first need to calculate the Simpson index and then just subtract it from 1. So in this case, if we take two sequences from the sample NT02 and apply the Gini-Simpson index by subtracting it to 1, we can say that the probability that these two species don't belong to the same, that the probability that these two sequences that don't belong to the same species is 0.67. So in this case, the Gini-Simpson index, their diversity is going to be higher if this index is closer to 1. And okay, another index that we are going to check at the practical session is Pilus index. So this one is in charge of measuring the evenness. The calculated value of Pilus evenness range from 0, that means that there is no evenness, to 1, that is a complete evenness. So this Pilus evenness takes into account the Shannon's index. The Pilus index would be the Shannon's index divided by the natural log of the number of species. So I know it was really quick, and I don't want you to learn all these formulas and maths, just you to know how does these indices work in general terms. So how is the alpha diversity represented? So we know that these indices often return slightly different results that could be visually compared with box plots. So just a quick reminder about what is a box plot. A box and this whisker plot would be the well-known box plot, and it's going to display the 5-number summary of a dataset. It will start with the minimum, then it's going to be followed up by the first quartile, then the median, then the third quartile, and at the end the maximum. So in a box plot, in this box, we are going to draw the first quartile and the third quartile, and in the middle of the box is going to be the median. So for some distributions or you will need more information than the central tendency measures. Just remember that the central tendency measures are the median, the mean, and the mode. You will need to have more information about the variability or dispersion of the data. So a box plot is the graph that gives you a good indication of how the values in your data are spread out. And finally, before going to the practical session, let's talk about the hypothesis testing. So statisticians usually develop their statistical hypothesis based on the research hypothesis that they have. So remember that you will have the null statistical hypothesis that, for example, it would be developed as there is no difference of the microbiome composition in health and disease, or whichever experimental groups that you have. Or also it could be that there is no difference or change in the microbiome composition in different environmental factors. This null hypothesis will depend on your project. But although these statistical hypotheses have the core theme that explores the impacts of environmental or richness of microbiota, they could focus on several topics, including the alpha diversity, that is the species diversity in each sample, but also in the bacterial richness in each sample. So an appropriate statistical method is needed to prove a scientific hypothesis. So briefly, some of the classical tests that are used in microbiome projects are these ones. The first is the standard t-test, that it's used to compare the alpha diversity between two groups or a population abundance between two datasets of relative abundance data. The non-parametric analogous of the t-test would be the Wilcoxon rank test, or also called the Mann-Whitney test, that it compares the alpha diversity of other non-parametric measures. Whereas when you are comparing more than two groups, one of the most common tests would be the ANOVA, or the one-way analysis of variance, whereas its non-parametric equivalent would be the Kruskal-Wallis test, if it's appropriate. It will depend whether the variables are usually or not normally distributed. So saying this, we are going to be back into the practical session. In this case, we are not moving back into the breakout rooms because I think it's better perhaps if you see the whole screen like you are looking at this right now. So I will just give the microphone to Violeta. She's going to conduct you into this other practical session. And if you have any question, you just can write it in the box of the questions and answers.
Hi. Okay, I share my screen. Maybe in this moment you have a folder with these files. Okay, a folder with data sets. We Nayeli show us how to obtain a rarefy object. The started file in this section of the workshop is phyloseq object RDS. So let's go. We need a new file with the option new file, R script, and OK. In this section, we are talk about alpha diversity metrics. Now that we have the phyloseq object rarefy, we can perform the alpha diversity analysis. We are going to open a new script, And again, it's a good practice to write a header at the beginning with the next, a general section. Remember, this is a good practice. Program alpha diversity metrics. You can, if you want, write a date. And maybe your name. Okay, we have a general section. Then if you, then please delete maybe the objects that you have in your environment with the little broom that you have in the upper right side. Okay, I don't have anything here, but maybe you have the older objects. Now we are going to call the libraries that we are going to use in this part. I am going to write a comment using the hashtag. Okay, other comment. And we need to call a lot of libraries, like library. Wait, sorry. Uppercase. Why? The first is phyloseq, then run, be patient. Sometimes take some seconds. Depends of your computer. The second is library, microbiome utilities. Library, microbiome. Okay. Other comment. Libraries associated with data or data manipulation. Tidyverse. Magritter. And DT. This is abbreviation. This is the meaning of this is data table. And libraries associated with visualization or plots. ggcurve. and run. Okay. If you don't see any error, we can continue with the next section. Working directory. And remember that this structure, hashtag, these scores, you can see in this part, maybe like a index, libraries, libraries, working directory, working directory. Okay. So we need to okay. So we need to configure the path of our working directory again, and I know that we already did this in the last section with Nayeli, but your scripts need to be functional for future executions. I am going to create the variable path and then copy as a string the path of the desired working directory. Path, a segment operator. And okay, this is my working directory. In this place, I see my principal file or object to import. If you are in Windows, sorry, I have Windows, but you copy and paste in this place your path. And if you are working in directory, remember to change the slash. If you have Mac or Linux, you don't have to change the slash. Okay. Then write the function setwd to adjust the working path, and inside the parentheses the name of this object. Then run. And okay, I don't have any problem, but remember that you can play with this section and to click to find the working directory, and then use this icon and set as working directory. This is a second method, maybe a graphic method to adjust a working directory. This is a line method or code method. Okay, I will check my working directory. And okay, I am inside the desired folder with the principal file that I need to import. Okay, I am ready to import the file with the next instruction. The new object to create is p is underscore rar use the function read. Remember, you have a file RTS, so we need to use a function to import this type of file, read rds. Okay, it is underscore rarefy point rds. This name is the same that I have in this folder. Oh, okay, sorry. Here, ps rarefy rds. Okay, you can see if you can see in this section in environment that the p is underscore rar is available. This is a large filosic created with Nayeli's section. Okay, and we have the basic elements: libraries, set the working directory, and import the rarefy object of the filosic, and then we are ready to calculate alpha diversity. Again, we write comment. Okay. To calculate alpha diversity metrics, we are going to use the function alpha that is part of the microbiome library. This function returns several metrics of alpha diversity. A new object is div of the diversity underscore alpha index. The function is alpha. Inside the parentheses, we can write the object that have the filosic rarefy. And we write argument index, and we will calculate all the indexes that the function can give us. With the with this information, all. Okay, and ready. You can see in the console the sets, the categories, the groups of the index calculate. We have a category of observer richness, other forms of the richness, diversity, evenness, dominance, and rarity. This object is a data frame, and we can easily check the call names. To explore this object about with the headers. And we can see 22 index. The Carla talk about that we see only few index like Simpson, Shannon, Pillow, but you can see a lot of index. Diversity index, evenness index, dominance index, index, rarity index. Okay. Now let's create an interactive table with the function data table of the DT library. To make an interactive table with this line. Wait. Mhm. Remember, this object has all the indexes, the 22 index. The results are shown in the panel and we can zoom it with this option. And this table shows the metrics per sample. Remember that each sample represents a community. You can show the 22 index ordered by alphabetic characters. C, D, D, E, D, and etc. You can show entries or samples, 25 entries or samples. You can adjust to see 50 or 100. You can sort by the scores, the minimum score of this index or the maximum score of this column. You can search samples. For example, I write, okay, see the names, NT, NT, TT, unsorted samples, and if you can filter, you can write some letters, maybe NT, and in this moment we can see only NT samples. Okay, we can continue write other characters. Maybe I write one, and we can filter the name with NT1 characters of the name of the samples. Okay, that's all. It's a interactive table. But if you want to export and save the file, click export icon and save and click save and click the option save as web page. Select a folder to save the file and write a name, table, um, alpha diversity index. Okay, September. Click save and check. It's here. Okay. Okay. If you want to explore more about any of these index, you must look at the documentation. For example, you can write something like that. Write a symbol like this. Okay, where is in my keyboard? Mhm. And a keyword like dominance, run, and see a technical section about dominance of the obtained by the library microbiome. And you can see a long description, but you can see another arguments, their descriptions, details. You can see authors, reference, and other links. Maybe some notes about the formulas. And okay, we can calculate an other metrics. Okay, not an other metrics. We can calculate a specific index with this structure, richness. Uh, this object is the original that we import in this section, but maybe we are interested to only calculate the richness index. Maybe we are not interested to calculate only the richness. And it's easy because only write the original object here in parentheses and then run. We can see the object and see all the samples in the first column. You can see only the richness index observed and chow. But if we are interested to calculate the evenings, right here, EV object evenings, P is rar, run, EV. And now we see the same samples and other index, Camargo, Pillow, Simpson, Ivar, Bula, and the last example is okay. I am interested to obtain only the dominance index. A new object, domin, dominance, P is rar, and then run. Domin. Da, 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 da. Run and check. Okay. We have we have the samples, we have a new columns of different dominant index, DVP, DMIN, absolute, relative, Simpson, core abundance. Okay. With this index, we are ready to make a visualization. So we can write a other new comment. Oh, okay, sorry. Okay, before to make a plot, we need to do a data preparation. Now okay. First, we need to do the next. Okay, data preparation. Okay. This object is maybe it's a complex from phyloseq, and phyloseq have is maybe like a list. Maybe has a like a layers. It's a complex object. We need to filter, to transform, or to get a specific data of the phyloseq object. This is a complex object, and we transform to a maybe a basic easy object, like a table, and explore the new object with a head function. Okay. Okay. First, we need to explore the div alpha, only to remember the structure, because I need that you see the columns. The last column in this object is rarity, underscore ray abundance, and the first column is observed, and the row names is the names of the examples. Okay. This line is to observe the div alpha object structure. Then we need to make some change with this with this code. Div alpha these symbols is to concatenate other instructions. Row names. Use this function, row names to column. We need to select a specific column. and see again div alpha to see the change. Okay. You can see a change here. We don't have in this position the names of the examples. We have a new column here. The second step is a merge with previous datasets and saving in a new object. Merge. The new object is div method with the function merge, and the objects to merge is div underscore alpha metadata, comma, space metadata, and the merge is by sample. Okay, other head function to explore the div meta object. And check. We can see the new column here with the header example, and we can see an other new columns in this section, sample type and accession. We have two sample types, normal tissues, and other samples are tumor tissues. We have two the subsets in the samples. And okay, we are ready to make a plot with the correct structure of the object. Box plot with one index. The syntax is based on ggplot. Remember, this is a pretty easy form to make plots with ggplot. Div meta. ggplot function as x axis. We select sample type. Remember, sample type has maybe two words, maybe normal tissues and tumor tissues. We have two groups in this sample type. comma, y-axis, and we select only one index. Maybe we can choose diversity Shannon because it's a traditional index. Okay, if you want to select an index, you need to write the same words that you have in your data frame. Where is Shannon? Where? Here. Only the characters are in low uppercase. We can see a underscore, and I write the same header here. Write a comma. Fill based on sample type. We can add an other layer. Select the geometry, box plot. We can add other layer, the theme. Add other layer with again like a theme, but we need to delete the legend. None, because maybe it's saturate the many. We have a lot of elements in the plot. None, and the last layer is labels. Y label is Shannon index. X labels is sample type. Okay, I think it's enough instructions to make a box plot. Then run. We can see the box plot and the results. This box plot shows the alpha diversity through the Shannon index in function of the samples type. In general, we could say that the samples from normal tissues have higher diversity, Shannon diversity, than the samples from tumor tissues, because the median of the red box plot that corresponds to maybe a 4.5 based on Shannon index is higher respect to tumor tissues. The median of the green box plot maybe is 4.1 maybe. Okay. We can make other box plot, but based in many box plot or based on many index, because maybe you want to see a lot of metrics in this plot. So write a comment, many box plot, box plot. Okay, the method or the pipeline maybe is the same. We need to prepare the object before to make a plot. So let's to prepare with okay. First, we check again the names of div meta, and we have a lot of index. So okay, I don't want all the index. I want to make a subset, then create a new object with a subset of the names of the index. Okay, remember to write the same characters. Okay, I want to select observe, comma. Maybe I want to see again diversity Shannon. Another interesting index is evenness pillow. Okay, another is diversity Ginny Simpson. And I want to, okay, where is, da, da, da. Okay, sample type. You can choose 3, 4, 5, 10, 20 index. You select that you need in your plot. Okay. Mm, Run to construct this vector. And then we filter div meta object with this vector. The new object is div. Okay. Operator. The principal object is div meta that has the 22 index, but we will filter with this selection and use the select function based on index object, and and check the new selection. Okay. observe, Shannon, pillow, and Simpson, and sample type. Okay, we have a new object. But okay, we can make another change. For example, I don't like this header because it's long. I don't want to see in my plot the underscore. I want to, maybe you want to write Shannon with uppercase, and maybe you can make an other change. So we create a new object with this change or modifications, names, index. Gosh. Okay. Okay, let me one moment to check the chat. Okay, I don't have any messages. Okay, it's all right. Okay, the new names of this maybe propose is observed features is the new word here. The old word is in this section. Maybe I want to write a new header. Maybe I don't like this long word. The new word is Shannon. A short word maybe is pillow. Mhm. Okay. And then to pass the vector that we already create as call names of the div data frame, call names, div names index, and right here div to see the new headers. Here we have sample type with this space. Here we have this column with Shannon, and okay. We need to continue with the format of the objects, and we need to transform with the next code. we select, this is a simple data frame. So we select only the first four columns with numbers or scores. 1, 2, 3, 4. The last column is a string data. So we select here the four columns with the scores. If you have 5 index, you need to write here 5 and etc. Names to index. And okay, run. And see the new object. We can observe new structure. In the original data frame, we have 5 columns, but in the new object, only we have 3 columns. Sample type, all the index, Shannon, Pillow, Simpson, etc. are in the second column with the name index, and in the last column has all the number scores, the numbers, and we have a new structure. Okay, this structure is ready to be input in a box plot. Okay, again, a box plot. No, many box plot. Many box plot with many index. Remember, the last box plot only has one index. So we can write the next digibox plot. This object. Maybe we can recycle. Let me think. Okay. No. Step by step. Sample type. Y axis. Okay. Sample type. Okay, here I will sample type. Okay. Y axis is value, comma, fill by sample type. Choose a color palette or palette color. This is a classic palette color, JCO. Have a categorical colors. Categorical colors is a selection of colors, especially to plots like a box plot. The legend I want to put in the right size. Grouping or facet by index and scales be free. Okay. Okay, example type. Okay, here is a okay with lowercase and the word type again and ready. Maybe all the arguments are easy. Maybe I need to explain something about scales. Scales, the meaning of scales is see or watch the plots in this box has the same size, but if you hear in this part we have different number scales, and scales just only adjust the size of the box plot with not in dependence of the numbers. Okay, this function this gg box plot is different of this section. This code is from ggplot library, but this code here, ggboxplot, is from ggpur library. Which else? Okay. Let's continue to making other plots. Box plot with header. We need a new object, box plot alpha index gg box plot. Use if long object comma. Okay, we can copy. Oh no, we can copy this code, and maybe you can copy and paste here. Okay. We use the same arguments. Okay, let me check. Div long, sample type, value, fill sample type, color palette, facet, scales, and we add a new argument. Okay, it's the same word, add, but with header. And we have initial parentheses, and we need to close the function with the end parentheses, and then run. Okay. But we assign in this object the plot, so we need to write the plot. Okay, header is an argument that can show you a dots. Each dot is a sample, and you can see the distribution of the samples of the dots in each box plot. But maybe this image or figure has some problems. Maybe it is repetitive. Maybe it's duplicate these labels. We have in the legend and we have in this position the same words. So we will delete these labels with the next code. Box plot, alpha index plus the function are remove. We want to delete x point x, this axis, x text plus labs Okay, I think it's right the code. Okay, and maybe looks well or plot easy, simple, with not redundance. Okay, the last section that we can apply in this workshop is a hypothesis test. Because, okay, I can see the colors, I can see the box plot, but is significant the difference if I apply a statistic test? This is the question. So write a new index or section in your script with the name of hypothesis test. Okay. We have some comments of this section. You must be careful about the type of variable you want or need to use. For example, you can ask the next in your project, does the index show a probability, for example, Simpson or Pillow? Does the index is a continuous variable, for example, Shannon? And remember that that we have parametric and non-parametric statistics. Carla talked about this in the theoretical section, but you have to consider if you have parametric or non-parametric statistics for continuous variables. And then I write two options to one with maybe a parametric code and other with a non-parametric statistic. So another recommendation is maybe to prove normality and the equality of the variance. So the first is wait. Sorry, I need to copy and paste a accent. Nayeli or Kenya, can you paste this accent in the chat if only if someone in this workshop can't find the character?
Sure.
Okay. Okay, the first step in this section is to make a hypothesis test. I select a t-test or t-student test. Remember that this analysis consider only two groups and maybe they have the same elements in each group. We have this characteristic in this data. And okay, okay, I forget a previous step because we will have error. We have to split before to make this analysis. We have to split the data here. Create a new object types with the function split and use div meta object and select meta and select diversity channel and again div meta and based on sample type. Okay, check object types to see the split. And it's easy. We can see only two subsets based on diversity Shannon. We can see here all the examples associated with normal tissues. And in the second part, we can see all the samples associated with tumor tissue. We have a split object here. Then we can continue to make a t-test. Types, select column, select object normal tissues here, and select of types the tumor tissues, and we can observe more sense or in this code. When you run this line, you can see the p-value. The result of this test is good because it's under the recommended value of p-value, which is 0.05. We are on under this score or value. Maybe it's a significant is significant the difference of these groups, normal tissues versus tumor tissues based on diversity Shannon using a t-test. There is another test. If you can perform a non-parametric test with this code, only change here Wilcoxon. Bueno, Wilcox is the abbreviated, is the short name or the correct number of the function. And you can see the p-value. We can see that is not significant, but it's okay. It's only a propose if you perform a non-parametric, but okay, we are working with the test. And write a comment because we want to make a box plot, but with this analysis of the t-test. Create a new object that can help the box plot. Create a groups is a list. Auxiliary object p-value. Again is a list. Okay. Good point. write the next numbers. I will explain in some minutes. You have to write asterisk. For asterisk 3, 2 asterisk 1, and end point S. From this, and maybe we are no okay. We are associate these values of p-value with symbols. These symbols will plot in the figure. If we have significant values, we watch or see not numbers based on p-values. For example, these values 0.001 and other numbers are significant, and we will see only asterisks. If we have non-significant values, we will see the label, and the meaning is non-significant. Okay, see, see, this is the last code. I will paste this. Okay. Remember, you will have the scripts in an email that Carla sent you. So I only copy this code to explain, because we see the code before. We can see the ggboxplot function. We have here the div meta. We can see the same arguments in the last section. So I can run again this, and observe that we have here the object, but I add a new layer. The new layer has a function with the name stats compare means. Observe that I indicate the method t-test. I indicate the comparison based on groups, which is the groups normal tissues samples versus tumor tissues. And the auxiliary object with the p-values and the symbols that I explained. Only we'll see the asterisk. Okay, and run. P-val. Okay, p-value is the name of the is the name of the object. I'm ready. We can see the box plot, but now we have a hypothesis test. We see the same that in the console. If you remember, here, when we apply the t-test, we see a significant p-value. The p-value is 0.002, and here, maybe here is okay. This is associated with this asterisk with this interval, and these asterisks with this interval and okay, etc. So one asterisk is in this section. So we can see only one asterisk. Okay, that's all. You can save the script with the name alpha index. And that's all. Thank you to be patient with me and the team. I don't know if you have some comments or questions.
Okay, so we have a comment from Sarah that she didn't receive any email. I think, well, the email are have been sent in behalf of the ECCB training. So I guess it's like all the way that you can reach us. We have like we put our contact email over there. But also before closing the session, I would like to share with you again the link that was sent through the email, that is this wintergenomics.github.io microbiome. And this link will have like all the information about this workshop, the scripts, the data sets, and everything that you need to recreate all of this info by your own whenever you want. So if there are no other questions or anything else, well, I think we just can't finish the session. And thank you, all of you, for your assistance and your patience and attendance. We are very happy to give this workshop today to all of you. But also, if you have any questions that wasn't completely clear at all, or that you would like to get in touch, you can also send us an email. You will find the email right on the website that I sent to you. And is there nothing else left to say? I would like also to thank you, my team, Nayeli, Viole, that we can see you right now, Kenya as well. And also we would like to thank the ECCB 2022 and Marina, that's been helping us today to make this workshop go through. So thank you very much, and I hope that you like this workshop a lot. So see you next time. Keep in touch.